In a previous section, you saw how to perform a quadratic regression. In this section, we're looking at in a more general sense how to fit models to data. It's important you know the basic shape of the different types of models in regression. Obviously, linear regression would be a line. Quadratic regression would be in the shape of a parabola, and trigonometric, the third main focus of regression in this section, would be periodic, like a sine curve. And you'd see similar shapes only with more bends in a cubic regression. Now, as far as your calculator is concerned, go to the Stat menu and go to Calc, and you can see that it will perform different kinds of regression: linear regression, quadratic, cubic, quartic. There's another linear regression. This form is more for statistics. This is more for your traditional math courses. The only difference is the placement of the coefficients. You also have the natural log regression, exponential, and then at the very bottom you have sine regression, which is what you would use for your trigonometric regression. So again, it's important that if you plot the data points and you see that it's curved, chances are you're not going to want to do a linear regression. If it's straight and it looks like it's linear, obviously you're not going to want to do anything but linear. You wouldn't want to do a quadratic or a cubic. In general, most of the problems from this section, it will tell you what type of regression you're going to need to do. So let's start by looking at number 10, where it's comparing Brinell hardness H of carbon steel when hardened and tempered at temperature T. Now, to start the regression, again go to Stat. We want to edit the lists, so just choose that first option. In list 1, we'll put the temperatures: 200, 400, 600, 800, 1,000, and 1,200. In the second list, put the corresponding hardnesses: 534, 495, and so on. And again, this is number 10 on page 34 of your textbook. Now, once you've entered the data into the lists, part A, it says to find a linear model for the data. So you'd go to Stat, Calc, and we'll use the more traditional form, the linear regression AX plus B, and hit enter. You want list 1 for your X list, and list 2 for your Y list. And if you look at part B, we're going to need to graph the model. So go ahead and, just as in the previous tutorial, graph the model by going to vars, yvars, function, choose the first one, and it will enter this linear regression model, the equation for this model, into y1 under the y equals menu, and then simply hit enter. So our linear regression, with y being the hardnesses, so you would end up with a model that uses y is H and X is actually T, our temperatures. So you would end up with capital H equals negative 0.3322857143, X plus 612.93333, and so on for your regression equation. Now it says to use a graphing utility to plot the data and graph the model. So we've already had it graph it under y equals, so let's make sure that that's there, which it is. And now we want to also, just as before, plot the data points. So you would go to second stat plot, which is just above y equals. Enter. Your scatter plot is your first option. Make sure that it's turned on. You have the type is the scatter plot, and that's fine. That's what we want. The X list is list 1. The Y list is list 2. Now again, look at our values for temperature and our values for hardnesses. So we're going to want to adjust our window. Let's go from just below that value. So let's go from 100 to 1300 for our temperatures. And then for our Y's, which would be our H's in this model, our hardnesses, let's go from, let's say, 450 to, well, no, hold on. Our lowest value is 217, so let's go from 175 to our highest value is 534, so let's go to 600. Then go to graph, and there's our linear regression. You can also, just as before, go to zoom, scroll down to 9, which is zoom stat, hit enter, and you get a similar value. Now on part B, the second part, it also says, how well does the model fit the data? Explain your reasoning. Well, let's look at, first of all, just the graph itself. It seems to fit the data fairly well. There's not too many very far away from our regression line. In general, we also want to look at the coefficient R, which is the correlation coefficient. In order to do that, with the TI-84, it would have been, if you just go to second quit, it would have been right here. With the TI-83 or TI-83 plus, we need to look that up. So you go to VARs, down to statistics, which is choice number 5. Oh, and then scroll over to EQ, which stands for equation, and then one of the options, if you scroll down to 7, is R, and that would be our correlation coefficient. And as it states in your textbook, the closer that is to 1, the closer the absolute value is to 1, the better the linear fit. So we hit enter, and it's negative 0.996. That is extremely close to 1. So our answer to part B would be that the model fits the data fairly well. It fits it extremely well, considering that the highest we can get is an absolute value of 1, and we're less than 4 1,000ths away from this being an absolute value of 1 for our correlation coefficient. Now in part C, it says use the model to estimate the hardness when T equals 500 degrees Fahrenheit. So again, go back to our graph, and let's look at our window first. And the value 500 is right in the middle of our values, so we're fine. You simply go to graph, second calc, value, and we went when x, which that's our t for our model, x equals 500 degrees. And our model estimates that the hardness, the Brinell hardness, would be approximately 446.79. And again, you can always use the table option as well. If you go to second table set, let's just start with 500. Go to second table, and there again is that same value, 446.79 for our hardness. And that's it. Other than you might want to, as mentioned before, let's go ahead and shut this off. Just press Y equals, scroll over to the equals, hit enter. When you graph the data points themselves, just go to, so we still have our stat plot on. If it doesn't say specifically that it's a linear model, you would want to look at the data points by themselves. And as you can see, it looks like it might be linear. There's a little bit of curvature at the end, but it would be a good idea to try to fit a linear model to it. So we were justified in using a linear model in this case, even before we knew what the correlation coefficient was or laid the regression line over the top of the data points themselves. If this was curved in a U-shape, then perhaps you'd want to use quadratic regression instead. And if it was periodic, such as most trigonometric functions are, then you would use the sine regression.